Alright, we're back. More collision stuff. Alright, so we've described a couple of things about how to do the collision detection between circles and rectangles, which is what you commonly need for 2D work. Is that sufficient? Well, maybe. I mean, if you say that you can take all the objects in your game and describe them as combinations of rectangles and circles, which in 2D you often can do, then in theory we've got the tools we need to work out. You can, if you get an elaborate shape that's made up of 2 circles and a rectangle hanging underneath it or something, as long as you can compute the intersection of those primitive shapes, then you can just apply that to create larger, more complex shapes. It's kind of obvious, but it doesn't necessarily work. There's actually a complication. What I've been describing up till now is a static collision. So this is the idea that I've said 2 objects have moved and their end positions might be overlapping, and you want to detect that and do something about it. That's true, but it turns out what really happens when collisions are occurring, of course, is that the objects, they used to be here and they end up here. And what might happen is, okay, they used to be here and they end up here, they're overlapping, you can detect it, do something about it. But what happens if they used to be here and they end up over there? Well, they end up in a final position where they're not actually overlapping, but they pass through each other. There should have been a collision, but they were going fast enough that they managed to pass through and actually ended up not overlapping. So there's not a static overlap, but they should have collided. Right? You understand? Yeah. So it turns out static collision isn't always good enough, depending on how fast your objects are going and how big they are. And you have to think about dynamic collision. So dynamic collision is this additional problem where you have to work out not just where the collision, not just where the object ended up, but you have to work out where they started from and the whole volume of space that they would have travelled through in between. So if you just use static collision detection and your objects are moving fast enough, they can in fact do this thing where they just warp through each other. Either 2 objects that go through each other, or potentially, imagine if you've got like a wall, like a corner on a wall or something, if somebody's going fast enough, they could go from being on one side of the wall right through to being on the other side, and it's like they should have hit the wall, but if you just move from here to here, they'll cut the corner, right? So that's a problem. So classically, in the literature, this is called the bullet through paper problem, because the easiest example to bring to your mind is the idea of you've got a bullet and a piece of paper, and the thing about bullets is they go so fast that even if your update rate is high, even if you're updating at 60 hertz, bullets are fast enough that it'll go from here to, let's say, here, and then the next update it'll just be out here. And it's like, if you do a collision check, is this overlapping with the very thin piece of paper? A rectangle and a small circle? It's not overlapping, and you move it and it's over here. Is it overlapping? It's not overlapping, so there's no collision. But unfortunately, you've passed right through the thing, and the paper could quite easily just be a body, unfortunately. So in a shooting game, this is a real problem. Like if you simulate the bullets go fast enough that they can definitely go from being in front of a person to being behind a person without ever actually going through them in a way you could detect. So you get a shooting game where like people hardly ever die because the bullets are warping through them, which is not good.
Couldn't you solve this with PIT-SCAN mostly? That there isn't actually a bullet, it's just...
Let me get to it. So this is the one to think about. Bullet through paper is the annoying problem where it's got a very fast object combined with very thin objects is the classic example where static collision breaks down, and you have this problem that, also it somewhat depends on your frame rate, right? The lower your frame rate, if you're only running at 30 hertz, then your objects move twice as fast per frame, so they become even more likely to jump through. So this is another thing where, depending on the frame rate at which your game runs at, you could get different collision behaviour. If you have a high frame rate, you end up catching the bullets because they go through the object. But if you're running slow enough that the bullet's moving a lot more than it would normally do, then it becomes more likely that you get a collision glitch. It's very annoying. So in theory, what you need to actually work out is not the static overlap of 2 shapes, but you need to work out the overlap of the volume that would have been swept out through space. So you imagine where the object was and where it's going, and you sort of imagine that whole volume that it would fill, and that's a bigger shape. So for a circle, it becomes one of these rounded cylinder guys, right? It becomes a lozenge. So the circle becomes a lozenge, and so does the other circle that it's maybe colliding with. So you get 2 lozenges, and you have to work out the intersection of 2 lozenges, which if you just think about it geometrically, it's a bit annoying. You can do it, but it's kind of annoying. This gets even worse. Like if you imagine imagine that there's like a cuboid or something, right? So a cuboid against a cuboid is a relatively simple thing to collide with. But if you've got the extruded shape, it's a cuboid being stretched through space and maybe even being rotated while it's doing it, which creates this like super complex shape that's hard to imagine. And it's very hard to do this exactly. So as I said, the linear sweep of a circle becomes this kind of capsule sausage shape, which you could deal with if you had to. Other more elaborate shapes, their extrusion through space when they move and turn actually becomes annoyingly complicated. So you can think about a rectangle. A rectangle being swept through space, it's kind of easy to understand what it looks like. It becomes a kind of, a big kind of boxy thing with with angled sides at all edges, but kind of with sharp bits at the edge. Just what a box would look like if you kind of stretched it out. It becomes this kind of clunky thing. So occasionally you need to deal with this, and you actually have to deal with swept volumes, but usually you don't. They're quite impractical. They're often hard to describe analytically. It's hard to write the collision code for these things. So often we don't actually do this. We just take shortcuts and make approximations again to just solve the particular problem that we care about. So a couple of ways of cheating or simplifying this problem. One of them is multi-step motion. So the idea there is that instead of having to calculate these extruded shapes, which are complicated, we just say, okay, if you were going so fast that the extruded shape is relevant, that you were where your end position and your start position didn't overlap, which means that there's an area in here that you pass through, but the collision detector doesn't know about it. You went from here to here kind of instantly. We say you've moved too far. So, and then we use a bunch of sub-steps and we say, okay, so you went from here to here in one frame, and that's too much. So I'm going to make sure that the collision system actually breaks that down into 5 sub-steps. So it goes from here, 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 here. So you just work out fractional steps, and that way you get a chance to check through all the intervening space. In case there was a little object here that you were going to hit, you just go click, 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 and you catch it. So you catch it on a sub-step. So a bit like when we did the collisions with the spaceships. You had some of the spaceships were running at dt divided by 4. They were taking sub-steps. So sometimes that's what you do inside a collision system. You say that my game logic's running at 60 hertz, but in order to be accurate, I want my collision system to run at 120 hertz. So you actually make it use internal subset. Just for the collision, you don't render these frames, but you compute them to check for the collisions sometimes. So that's one way of doing it. You just time step it so that the gaps are small enough. And you can do it adaptively as well. Instead of saying you're always going to use 4 sub-steps, the number of sub-steps is potentially you can make it depend on the velocity of the object, right? So basically you want to make it so that the sub-step is of a size such that the object can't kind of move more than its own radius in one sub-step. And if you just say, so that means that fast objects, you break them up a lot so that they go in many sub-steps, and slow objects, you don't need to break them up because they're already moving slowly through space. So that's kind of how you can do it. You can say, compare my current velocity to my size, and if I'm moving faster than my own size, then start using sub-steps. And that allows it to kind of just fill in the gaps a little bit. So you can do things like that, yeah. Don't move by more than your own radius, or don't move by more than some small amount of time if you've got a particularly fast-moving object. The other things you can do, sometimes there is a natural kind of maximum velocity to an object, and that way you can just kind of compute ahead of time what the right sub-step should be. So one example is you take cars and stuff like that. The speed that a car's moving per frame is almost always going to be less than its full size. So you don't really have to worry about doing many sub-steps on a car usually. But there'll be other objects where the bullet's the classic example, or maybe a fast-moving projectile, like a grenade is a better one, right? So a grenade is something where, grenades can obviously move more than their own length per unit time. So you would say, okay, in the grenade code, use sub-steps. But some of the bigger, slower objects, they wouldn't have to usually, because in practice they don't really move more than their own length in one update step. So it turns out for a lot of things you end up ignoring this problem, because in practice it doesn't matter for most things. It matters for some things. It matters for grenades and bullets, but big objects, generally speaking, it's not that big a problem. But if we go back to bullets, they're a classic case where you really do have to care about it. But luckily, bullets are simple in other ways. Bullets have got the advantage that they're sufficiently small that you can pretend that they're almost points. So with the special case of a bullet, instead of having to work out like what a sphere or a little cylinder, what the real shape of a bullet is, working out how that's extruded through space, you can say, just treat it as a point. So it's a point that was here, and the next frame it's over here, and here's your piece of paper, right? So what you do is instead of checking for collision with the point and the point, you draw a line between the previous position and the next position, and now you're just checking a line against the piece of paper or the body that's between them. And it turns out line checks are something you have to do anyway. Line checks are not that hard, and you need to do line checks for like your graphics system. The lighting system is always doing this. It's having to work out whether lights can, whether a particular light source illuminates a certain part of the world. That's a line check. Whenever you pick things up, if you use a mouse click to click on something in a 3D game, what's really happening is that when you click the mouse, it's a bit like you're kind of having to project a line from your eye through where your mouse is into the world and work out where that collides in order to work out which object you're touching. So you need to be able to do line checks anyway. So it turns out for bullets, you just take advantage of the line checking collisions that you've already got in the system anyway. So, and there are standard things for this. You can go in, standard geometric solutions to work out whether a line intersects with a sphere, a cuboid, a triangle. You often have to do it at the triangle level because you might be colliding with the environment and the walls of a building that really are probably made up of triangles. So you just do a ray triangle intersection. All right. So let's think back to 3D. So the 3D equivalent of our basic primitives are cuboids and spheres, and also convex hulls, which I'll talk about in a bit, and maybe cylinders and things. So cuboids and spheres, they're a lot like the 2D. Like if you want to work out whether two spheres collide, it really is the same as the two circles, where literally you just add one more d, right? It's instead of x squared plus y squared, it's x squared plus y squared plus z squared. But it's geometrically it's very similar. And again, the check for cuboids is just like the check for rectangles, except there are more of them. You have to do it for all, the 8 faces, 6 faces. Yes. The other thing you'll notice is that in the real world and real games, there aren't that many things that you would look at them and say that they're clearly spherical. Things in games tend to be a bit kind of boxy. But spheres are so much faster and easier to deal with than rectangles that often we use spheres anyway. So what you can do is you can take like an arbitrary volume and just fill it up with spheres of different sizes so that it's a reasonable approximation, because the spheres are so fast to compute, they're much simpler than rectangles. So in fact, a game I made back in the late 90s called Wild Metal Country. It had lots of dynamic objects in it. And was largely based around tanks, and the tanks are fairly, squarish kind of rectangular things, but actually all the collision that we used for the tanks in Wild Metal Country was actually done with spheres. So the idea is that the tank would look as if it was a box, but we tended to think of it as more like an egg box, how it looks a rectangle, but it's actually just got six spheres inside it. That's literally how we did it. So when the artists created the models, they'd create like the visible geometry that we could see, and then they would create a simplified version that was just made of spheres, and that was the one that we used for our collision detection. In fact, this is what EVE Online does as well. The spaceships in EVE Online, even though a lot of them are like very obviously angular and squarish and long and thin, they're all done with spheres. For the very extremely long ones, again, it uses the trick of there's a bounding sphere that just catches the whole thing. But if you go inside the bounding sphere, there's then like maybe 4 or 5 spheres along a line that represents the shape of the thing, but it's actually all sphere-based rather than being cuboid-based in the way you would maybe expect it to be, which I think is a little bit embarrassing. Sometimes you can see this, that there are anomalies in EVE because the ships are all made of circles, but that's just the way it is. And it's been that way since they first made it, and it's occasionally there's talk about trying to improve it, but it's never been the highest priority. And because you don't do a lot of close, you don't do a lot of direct collision in EVE, the combat's always done at a distance because you're using ranged weapons and lasers and stuff. They get away with it. Yeah. So triangles are an interesting case. So obviously most stuff in 3D games, ultimately it's all made of triangles, right? That's how 3D works for now anyway. There are other potential ways of doing it, but generally things are made up of just large numbers of small triangles. But you tend not to use triangles in collision detection because they're just a little bit, well, there are a lot of them and it's a little bit annoying. You can work out whether you intersect with a plane quite well, but to work out whether you intersect with a triangle, it's actually kind of a little bit annoying. You have to work out exactly which part of the plane you intersected, and is that plane on the inside or the outside of the triangle? A little bit irritating. So you don't normally use triangle level collision, but for some things you do. One thing is if you've got like an outdoor terrain environment, you really kind of have to represent it as made up of triangles because if you wouldn't want to approximate a rough terrain as being made out of spheres. Because you'd be bumping up and down these kind of slightly invisible eggshell spheres every time you drove, right? It's not going to work. You've kind of got to make the ground feel sort of flat, but also has to be able to bump and undulate. And I don't think there's really a good solution to that other than essentially making it be made up of lots of triangles. And then in dungeon environments as well, the walls and the floor of a dungeon, they're usually just treated as like big triangles. So you do in fact have triangle collision for some things. Right, yes, convex hulls. How many of you don't know what a convex hull is? At least a couple, right, most of you. It's one of these things, I wasn't sure if you've been taught. You maybe know it when I show it to you. Maybe it's got an Icelandic name, I don't know. So a convex hull is, it's basically, if you imagine taking some arbitrary shape, like the bottle here, right? Do you know the difference between convex and concave? You know those words, right? So the problem with this bottle is it's got bits that are concave, bits that bend in, right? That's a concavity. It bends in, right? Those any sections. If you wanted to make a convex hull around this thing, it's kind of like you'd sort of shrink wrap it, but so that with stretching cellophane over it, so you would end up putting it over here and down here straight, right? So it would be kind of bounded by a shape that doesn't have any parts that bend in. It's only got convex parts. It turns out that the geometry for convex shapes is a lot easier than when working out concave ones. So what you often do is you take a shape and you put a convex outer shell on it, and that's the one you use for collision detection. So I can show you that here, in fact. So if you see this little thing here, maybe make it, no, that's not right. Okay. So if these were the points of your object or something like that, right? What you would do to make a convex hull is you kind of imagine, let's say, shrink wrapping it. This is the shrink wrap here, or like in 2D, it's like an elastic band, right? You take the elastic band and you allow it to contract until it contains all of the points in your shape, but it contains them in such a way that the result is entirely convex, and that's a convex hull. You can see a bit more about them in the wiki article, but I think that's enough. And if you just search for convex hull and look for the images, you'll see what I'm talking about. Yeah, you can see this kind of thing here, right? Where you just draw that nice boundary. So here's an example of the difference between them. The good thing about a convex shape, I've lost the image, that's annoying. Hold on, I'll go back here. Is it buried away in here? Right. See, if you made a shape like this, so it's got the concavity on it, then that violates the rule. This is, this correctly bounding all of these points, but it's got a concavity, which means that it's not a convex hull. The rule about convex hulls is that if you take any 2 points inside a convex hull and draw a line between them, the line is inside the convex hull itself. That's the basic distinction. And it just turns out mathematically that lets you do things. So that this one here is the convex hull around these points, and this is a non-convex hull. So the cute thing about a convex hull is it's easy to do a check whether something is inside or outside of it. Turns out you're inside a convex hull if you're on the inside of all the planes that bound the hull. So the simplest one is like a cube, right? A cube's a convex hull, And the way you work out if you're inside a cube is if you're on the left side of the right edge and the top side of the bottom edge and the right side of the left edge. If all those things apply, then you're inside the cube, right? And a convex hull just extends that to thing that might have 20 faces. You know, it might be like a dodecahedron dice. Well, that's 12. Icosahedron is 20. But imagine if it was like, it had multiple faces, but it's the same logic. You go through each face, and as long as you're on the inside of each face, then if that's true for all of them, then you're inside the shape. It turns out it's fairly quick to calculate this. So that's Unreal. I don't know about the latest one, but Unreal 3 certainly works this way. That for some shapes, what it does is it calculates a convex hull of them and then uses that to check whether you're inside them. And this is quite a nice thing. It also means that if you've got a shape that is not convex, you can break it up into parts that are convex. So you can always kind of decompose something into convex hulls. So they're turned out to be quite a good class of boundary shape. So another special case that comes up in games a lot is humanoids. Humanoids are kind of an annoying shape because, you know, we're not really cuboids and we're not really spheres. It's a bit annoying, but sometimes actually sphere approximations do sometimes work. Sometimes humanoids are just treated as a number of spheres stacked on top of each other, you know, like a snowman. You know, three spheres, which is okay, but you can tell it's obviously got limitations. Like it's not good at dealing with outstretched arms and so on. Another common one is upright cylinders, which again is what Unreal used to use and probably still does use. So although the body is articulated and quite detailed, for most of the game collision logic, it's just treated as if it was a cylinder that's always standing upright. In fact, even if you're slightly tilted or you're crouched, it always treats it as a cylinder. And a cylinder is just a circle that's been extruded along a line, so it's not that hard. Yeah. The other thing that can come up in 3D collisions is you can have hierarchical objects. So that's objects that have got like movable joints, again like a human, where you've got a skeleton of things that are linked together, and each joint's got a matrix that defines how that bone rotates relative to the parent bone. It goes all the way up. The annoying thing there is that you might have a collision volume for each part, you know, for the hand and the lower arm and the upper arm. You have all these different parts, but when they're moving around, they can be in some other configuration. And you often want to have a bounding volume around them, but the bounding volume is potentially going to change in size. You know, if you're standing still, your bounding volume is tighter than if you've got your arms out. So it can sometimes be annoying if you've got a shape that's hierarchical to work out what the exact bounding volume ought to be. But the simplest one is just to say, just work out what the maximum spread is. So, you know, work out what your figure, if you posed it at full stretch, and work out what the bounding sphere would be for that. I just use that one all the time, which is slightly inefficient because a lot of the time you're actually much smaller than that. But the alternative is you either have to use like a different bounding volume depending on whether you've got your arms out or not, or you have to dynamically recompute the bounding volume, which is a bit annoying. But that's something you have to think about. So if you've got like a hierarchical model, you have to work out what its most splayed out extent is, and then make your bounding volume work around that. So that's a little subtlety. Yeah. So this is just what I was saying there again, that your parent volume might have to be recalculated from time to time to deal with the actual position of the inner volumes, because sometimes you might think that the arm is constrained by this volume, but if you swing it out, it can go outside the bounds of this thing. So it's just something you have to be aware of. Right. Another special case in 3D is the game environment. Now I mentioned before that, there are a couple of points here. So first of all, generally speaking, collisions are comparatively rare. You know, most of the time you're not colliding with other things, but it's, you know, obviously you do from time to time and it's important, but you're maybe only colliding with other normal objects, maybe 1% of the time, but you're colliding with the environment almost all the time because usually you're standing on it, right? So you're actually colliding with the terrain on every frame, and so is every other object in the world, pretty much. So it's actually important that your terrain collision be efficient, because it's happening all the time for every object. It's very true in vehicle-based games. Generally speaking, in a vehicle-based game, you're in a state of constant collision with the ground, but what the ground is doing is applying a force on the wheels of your vehicle to kind of push you back up and keep you out of it. But every frame you're having to work out exactly what that force needs to be, so you're having to track the terrain quite closely. Yep. So as I touched on earlier, environments are kind of annoying, that they're very big, and generally you can't really simplify them very much. You can't treat them as spheres or as rectangles. That doesn't work very well. So you actually have to treat the terrain as what it really is, which is to say, it's a ton of triangles. It's sometimes called a triangle soup, right? So you really have a triangle level model of the world, and that's almost the one that you have to use for collision detection, and it makes it a bit of a difficult case. So we can't use the simplifications of spheres and boxes very easily. So because it's important to get terrain right, because you're colliding with it all the time, and because it's by its nature kind of has to be done at the triangle level, which is also quite complicated, there's a strong incentive to try and find ways to simplify, because if you don't do anything about it, it would mean that every moving object is having to do collision checks against your terrain on every frame, and your terrain is built of tens of thousands of triangles. If you really want to be going to iterate through tens of thousands of triangles and doing these kind of non-trivial collision checks with them, it would be horrible, right? So you've got to do something better than that. So here are the shortcuts. One of the classic shortcuts for terrains is a thing called a height map. So what you do with a height map is, instead of treating your terrain as a completely arbitrary set of triangles that an artist has made, what you do is you think of it instead of as a grid of points. If you imagine viewing it from the air, right? If you view it from the air, it's like a grid of equally spaced points along, we'll call it X and Y. And each one of those X and Y points, you just have a height value, which is the Z. So it's actually it's a grid as you would see it from above. And that makes it a lot more regular than if it had just been an entirely arbitrary set of triangles. So there are a couple of things that you gain here if you make your terrain a grid. For a start, the memory savings are quite large. Instead of having to store a lot of triangles, each one of which has got like 3 points that you have to specify in full XYZ, most of that you don't need to specify. You only need to specify the Z's, just the heights of the grid positions. And the X and Y's are implied because it's all done on a grid. So it's a lot like Breakout, right? It's how in Breakout we didn't really store the bricks. We just allowed the wall to be a grid that shaped it all. And this also helped with collision detection, because when you were doing a collision, you didn't have to check against every brick. You just knew which part of the array you were on, and you just checked that. Well, imagine the same thing, thinking about the terrain as viewed from the sky. So from the aerial view of the terrain, it's a big grid like a wall, and each square on it is like a little brick that's only got a couple of height values specified at the corners. And it means that when you're working out how to detect the terrain, you just work out which part of the terrain grid are you on top of right now, and you jump right into the array at that point. And basically, you go into that point, you just got 2 triangles, because you'd always be inside a square, and the square's made up of 2 triangles. So that's how it's done. So again, Wild Metal Country, my tank game, worked this way. We had a grid-based terrain, and it turns out that's what Skyrim did as well. Those games, even though they're a lot fancier and they hide it better, because there are things you can do to blend to kind of conceal the gridded nature of the thing. But it turns out Skyrim was actually based on a terrain grid system. So the way you create these height maps as well, you can do anything you like, but a thing that I actually did is initially created the terrain using a fractal. You know about fractals? Are they still cool? Kids still like fractals? So you can set up the heights at the corner of your terrain map, and then you tell it to just subdivide it into 4 subparts, and then interpolate the heights in between and add a bit of random noise to them and just generate new heights. And then you do that recursively. So you recurse through the whole terrain and you just invent heights, and that way you can create a whole terrain very quickly just by specifying some corner positions and a random number seed. Or the other thing you can do is you can let the artist draw the terrains by just drawing a grayscale image. So you just let them paint, look at something in Photoshop, where black means low and white means high, and they just paint a grayscale image, and then you turn those pixel colors into heights, and that way they can just kind of do like a brush to say, I want a mountain range, so they just do a white area, and that's a mountain range, and they want a valley, and that's a black line, and they just paint those things in, and you convert them all into heights. Or you can create an editing tool where you let people manipulate the height grid. So there's a thing where you could write a program that would allow them to go and like pick up a part of the terrain and say, okay, I want to pull that part of the terrain up and bring up that part and the bits that are around it, and it would just loft them all. So I've actually done a combination of all three of these things. With Wild Metal, we created fractals to create like a baseline environment, and then we allowed the artist to go in and customize it to make it, satisfy whatever kind of gameplay qualities they wanted. The other thing you have to do with height maps is you have to decide how to texture them. The old way that this would be done is that, so you've taken your terrain and you've said, okay, my terrain's going to be a grid because that makes life easier, and now you have to work out how to fill in actually the visual detail. So the idea is that you would have a set of terrain tiles for different material types, like rock and ice and mud and all this kind of thing, and you just plank those down in various parts of the terrain. The problem was that the joins could be tricky because it's actually all a grid. So there's a point where if you go from mud to ice, you'd have this kind of straight line that's a little bit too obvious. So what you would do is you'd get the artist to create special tiles that would basically make that represent the junction between the two different types, the join between the ice and the mud, and they would just draw it so that the edge was kind of blended over, or not as linear as it really was. They'd make it look a bit jagged or smooth or something. You can do something better than that with texture blending nowadays, where you could actually say that you can tell the graphics cards to kind of draw two textures on top of each other and kind of blend, like alpha blend between one and the other, and that sometimes produces nicer looking joins. That's I think what Skyrim does. But Wild Metal was old enough back in the late 90s that the hardware couldn't really do texture blending, so we didn't have the option most of the time of doing smooth blends. So we had to do a thing where we'd try and let the artists would try and draw some of the blends, but also we'd have to just algorithmically pick tiles that were, we'd create transitional tiles that were like 50% ice and 50% mud, and at the join between the different terrain types, we'd try and pick the blend tiles that fit the best fit for the relative composition of the materials. So I'll show you a bit of what that looked like. So you can maybe already see here, you can see like this fairly conspicuous line down the world. That's the seam of one of the lines on the terrain grid, because you can see that that this tile and this tile, they're not exactly compatible with each other, but that's kind of how it's done. And you can see the repetition as well, but that's because limited memory. We only had like maybe a dozen tiles for each surface type, and we had hundreds and thousands of squares to fill, so obviously some of them are reusing the same image. Another funny little thing about this game is just at the start here, when we're previewing the map, we preview it and show you a wireframe, right? But because the whole game was 3D based and everything like that, we didn't write a wireframe renderer. So this wireframe here is actually fully solid 3D with a special texture that's just black with green around the outside of it. So that's a fake wireframe that's actually drawn using solid graphics. So again, you can see the seams are fairly obvious. This is a big giveaway that you get in height map based games, that they've got these seams. But as I say, modern games are better at hiding it than we were, because they can use texture blending to kind of smooth over the sides. So what's going on here is that this tank guy here, as I say, he's actually, the collision system treats him as a bunch of spheres, maybe 4 spheres or something, and those spheres are collision checking against this terrain grid. But all they do is you take the center point of the sphere and you turn that from a coordinate in space into a tile index, just like we did in Breakout, right? You just divide it by the width and the height of the terrain tiles. So that position, whatever it is, ends up being 15 by 12 on the terrain grid, and then you go to the terrain array at position 15 by 12, and you actually take that position and its neighbours, right? It's got a position and 3 neighbours, and you take out those height values, and then the system kind of works out what the 2 triangles are implied at that square, and it then just works out whether the spheres would have intersected with those triangles or not. And if they do, there's a little force we apply on the wheel, which acts on the suspension and pushes the wheel up. And that's what keeps the thing from falling into the world. Basically, the suspension is constantly being pushed up by the terrain, and it's kind of springing the system, and that's what keeps the tank on the top of the world. Yeah, really primitive. The fog was another trick. The further, there's just a thing where there's actually a colour palette here because it was palletized rendering, where the further away things are, the darker you blend them to like a sky colour. But I'm not going to explain it, it's too much.
That's a battle though.
Yeah. And you can also see these the tanks leave trails behind them on the ground there, and those are just drawn as an extra layer on top of the terrain. So we draw the terrain normally, and then there are these additional textures that have got the tracks from the wheels, and those are just stored in a list. It's a bit like the trail from your pong ball, right? When the tanks move, they leave behind a pixel trail that we store in a bunch of textures, and we haven't got infinite memory, so the trails don't last forever. But each tank would have 20 tiles worth of terrain memory that they would leave behind them, and we just draw those on top of the basic terrain, so they would leave the tracks. So you can see it's kind of primitive. I mean, this game's like over 20 years old now, so there are some kind of historical deficiencies on the rendering quality, but that's basically how it works. And this is not uncommon in outdoor games that actually it's a terrain grid underneath it all. So they say Skyrim. I mean, Skyrim's a bit old as well now, but it was a much more recent game, and it used the same basic ideas, but was better at hiding the joins because they had texture blends. And it turns out there's a tool for Skyrim for creating the terrains that does a bit like what the tool we had for WMC has, where you can go in and you can loft up hills. I'll show you because it's quite neat. It takes a while to get going, I think. Right, so it zooms in at some point, and then you can actually see this is the terrain surface here, which is just the same texture being repeated over and over. So at that angle there, you can kind of see the regularity of it. It's the same thing over and over again, but in practice they do enough to put in variants and blends that this becomes less obvious when you're actually inside it, if the level's been well designed. Yeah, I don't care about that part. So zoom out again, this ridiculous repeating tiled grid thing, and now he's painting in a new texture. It's painting in water, so you just look a spray paint tool. So what's happening here is that the terrain system for each tile has got something that stores not just the height of the points, but also what material is this? Is it rock? Is it water? Is it grass? And the idea is that each tile is potentially like a blend of different terrain surfaces, and you can basically apply like a spray painting tool where you'll add more water content to this tile until it becomes more water than anything else. And if the largest component of the mix is water, then it uses the water texture. If the largest component is grass, it just uses the grass one. So they're using like a spray brush tool here that's spreading wateriness out in the grid so that more and more tiles are becoming predominantly waterish.
In this case, we don't have two different heights to define where the water is.
Well, water's a special case because water has to be kind of at a flat level. So yes, there's maybe a trick to make sure that water levels are set.
That's and also the ground true. Under the water.
Yes, that is true. They might preserve the ground underneath the water. But if you think of instead of the water, if they were spraying ice or something like that, it'd be kind of the same idea. You see they're changing the height here, so it's just like saying that they wanted to raise all that terrain to a particular height value, and it's just been all dragged up. And then at some point they'll actually loft up a mountain by picking that. There you go. So you pick a point and you say, okay, I want to make a hill here, and I want the radius to be whatever, and you pull up the point, and it just works out. The further away you are from that point, the less height loft you get until it fades off eventually, and it just allows you to pull up big mountains very quickly. So it's a lot easier than modelling it out of triangles. So it's also faster for creating environments. Okay, so that's that. So that's sort of how you create gridded terrains. And here's an example of a texture palette that you might use. So this is where you tell the artist to make something that's like 100% grass, and then you say I want one that's 100% grass and 20% sand, and you try and create a bunch of these mixtures. And the idea is that then your terrain tool stores the composition mixture that each tile has got, and then you look in your tile atlas and you pick the texture that's the best match for whatever mixture you happen to have. So this is a kind of crude way of doing the blends. Although, as I say, that it's slightly better if you can also use texture blending, which allows you to superimpose different textures on the one place and make them join in a kind of smoother way than this. All right, so that was 3D terrains and 3D environments. Well, let's flip back to 2D. You can do equivalent stuff in 2D. Remember, in 2D, if you've got like a platform game, you're doing it side on. You've just got a 2D grid of background tiles that represent, the platforms and the walls of the environment. And it's the same thing. When you move the character, you just work out where they are on the environment grid. You index into that, and there's just a flag for each sprite that says whether it's solid or not, so you know whether it's a place that you're not allowed to go to or you are, and you just work out simple collision based on that. So yeah, grids are very commonly used to allow all this kind of thing. The good thing about grid is it allows you to very quickly find the thing that you care about by indexing into it instead of having to search. Otherwise you'd have to search through like the list of all the blocks on the level to work out whether you happen to collide with anything. You don't have to. You just work out where am I in the index, and is that a solid block or a non-solid block? Again, just like Breakout. Okay, so that's about the end of that. Now, you'll notice I haven't actually specified the homework yet this week. That's because there will be a homework, but it depends on stuff that I won't be able to get around to until the Wednesday lecture. It's some more stuff about collision details. So unusually, the homework will actually be announced on Wednesday. Hope you don't mind. I think I'll make the handout date will still be next Monday, just to keep the rhythm of the marking. So it's slightly less time. But I don't think too many of you really start the homework on the Monday night anyway. You only have to wait till Wednesday, and we'll just go straight into the tutorial on Wednesday where you can start working on it. So I hope you're not too disappointed at not getting a homework exercise yet, but don't worry about it, there'll be one, probably. And that's the end of that. Again, I'll spare you the video, unless you particularly want to yourself. Okay, we're done.